Today we discussed regarding the syllabus of Verilog HDL. So today let us discuss regarding the corresponding course outcomes for which POs as well as PSOs it will going to map. So first we let us consider POs. So when we are going to consider POs, there are basically 12 PO. PO is nothing but program outcomes. So when we consider the first PO, engineering knowledge is nothing but the basic knowledge required to understand this subject. Okay. So if you are able to understand this subject means you will be able to acquire the corresponding engineering knowledge. And next what we are having is problem analysis. So using this subject, how a problem can be analyzed. And next let us have the third CPO, that is nothing but design or development of solution. So when you are able to analyze a problem, then you will try to develop solution for that problem. So that comes regarding design and development of solutions. The next one, what we are doing is after developing a solution, then we have to check whether our solution is correct or not. If it is not correct, once again we have to do redesigning, isn't it? So that is why the fourth PO is conduct investigations of complex numbers, complex problems. Next, the fifth PO, what we are having is usage of modern tool. So when you are finding any solution for particular problem, whether you are using any modern tool or not, so that we are going to consider. And the sixth one, what we are having is engineer and society. So whatever the problem we have identified and the solutions we have designed as well as the solutions we have obtained, whether it is helpful for the society or not. If it is not helpful, so once again we have to think of the solution. Otherwise, that solution can be used for the welfare of the society. And then third one, what we are having is environment and sustainability. So whenever the particular solution has been developed, so in that case, we have to think of how much eco-friendly it is and also how much our solution is sustainable. So if our solution is not sustainable for all context, so in that case again this will not going to give a proper solution. So that is why we should think of the corresponding sustainable solution, whether our solution meets the requirement. Okay, and how long that particular solution can be used. So all these things we can consider. And the eighth one, what we are having is professional ethics. So when we are doing all these things, whether we are considering any ethical issues. And and the ninth one, what we are having is individual and teamwork. So while providing all these solutions and while considering the usage of any modern tool for the solution or for problem analysis and all, whether we are doing the work individually or whether we are going to do in a teamwork with teamwork indicates that when we interact with multiple departments or when we interact with multiple types of solution, there the maturity of the solution will going to increase. So for that we have to involve with the other group of people, so that where our solution is required and whether this can be um, useful or not. So that analysis, to do all these things we need a either team or we can do individually through surveys and all. And the 10th one, what we are having is communication. So whatever the design we have done or whatever the problem we are analyzing, first we have to come up, I mean we need to discuss whether any particular problem or design is required. All these things, sorry, any particular solution or design is required, and whatever the solution we have developed, whether it is mm, uh, affordable, sorry, whether it can be used or not. So for all these things we will be interacting with the people or society. So as a result, when we or else we may be doing some teamwork. For example, if you are going to consider any building construction only, so there only individual person cannot complete the entire building as soon as possible, isn't it? You need many helpers. So in such case, it is considered as a teamwork. In the same way, when we are going to develop any solution, there may be a teamwork or an individual work, it depending upon the complexity. So when we are doing all such things, we need to communicate with the people who are facing the problem. Okay, so for that, the when we perform the when we try to interact, will our communication skill will be developed. So for that, we'll going to consider whether our course is helpful in this particular attaining in this particular view. Similarly, next what we are having is project management and finance. So when we are going to conduct any investigation and all, so in that case, whether we are considering a particular project or whether we are developing a project, whether we are getting any financial support to develop this particular project, all these things will be considered in this PO. And the last PO what we are having is lifelong learning. So whatever the course we are going to learn, whether it will be helpful after the course or after the program, after the completion of your program, and when you go outside for a job and all, whether this will be helpful or not. So like this we are going to consider the POs. So and program specific outcome, it mainly depends upon the program which you have chosen. If you are choosing civil engineering, it will be having its own specific outcome. Similarly, when you are selecting electronics program, it will be having its own specific outcome. All the departments cannot have a common specific outcomes, okay, but in general the POs what 12 we are having, it can be attained. But when you are doing specialization in a particular program, every program will be having its own specific outcomes. So in our program, we are having two PSOs. One is specify, design, build, and test analog, digital, and embedded systems for signal processing. Then second one is understand and architect wired and wireless, analog and digital communication system as per specification and determine their performance. Okay, so now let us see how our course outcomes or course, yeah, will going to map for these program outcomes. So regarding course learning objective, we discussed in the last class only. Okay, what is the objective of this course? So in our course, we redesigned some course outcome. So there in the syllabus around 6 course outcomes are there, and here we have reduced it to 5 outcomes. So the first one is you'll be able to write programs in 4 different levels of abstraction. And the next one, whatever the program you have or whatever the design you have done, you will be checking the functionality by doing simulation. So while doing simulation, you may consider the corresponding time delay of the device, or you may not consider. So that is why the time delay and all comes under the second CO only. And the third one, what we are having is identify the suitable level for a particular suitable abstraction level for a particular digital design. This also we have discussed yesterday. And the next one, what we are having is writing program more effectively using Verilog tasks, functions, and directives. Fifth one is interpret the various constructs in logic synthesis. So now we have to identify how our course will going to map the corresponding POs. So when we are studying this course, we will be able to acquire the engineering knowledge. So the first CO, because basically the first thing what we are going to do is how to write program using the HDL language. So that is the basic engineering knowledge we are going to acquire. So that is why CO1 mainly maps to the basic engineering knowledge. Here we are not investigating anything and all. So that is why it will map to only program outcome 1, which is nothing but engineering knowledge. And the second program and the second CO is design and verify the functionality. So if you are able to design, means you might have understood the problem. If you know the problem, then only you will think of the solution. So if you think of the solution, you will try to design the circuit. So when we are designing, means it's understood that it has attained PO2 also, PO1 as well as PO2. If you are having engineering knowledge and if you are having analysis capacity, analysis of problem capacity, then you can able to design. So that is why we strongly map CO2 for PO3. So after developing the design, you will try to analyze whether your design will going to work properly or not by doing simulation. Since this is a lab supported subject, means whatever the programs you are going to study in theory, or the same programs you will be executing in lab also. So as a result, we are using modern tool like Xilinx to execute the program and understand the concepts clearly. When we are doing this problem analysis, designing the solution, testing, or that is nothing but verifying the functionality and working on the software. So for all these things, we will be using either individual work or teamwork, especially when we have given a tasks or when we are doing interfacing and all, mainly we will be using teamwork. Or else if there is any errors and all while writing the coding and all, you'll be communicating with your friends and you'll be trying to analyze the program. So as a result, this strongly maps to CO, I mean 3, PO9, CO2 strongly maps to PO9. Similarly, it also maps to PO10, because I told if your design is not working properly, then we will be communicating with each other to find out the proper design. So as a result, communication skills will be improved. So CO2 maps to PO10 also. And the next thing what we are having is CO3. So again, when a particular design is asked, so if you have given a problem to find solution or to find uh, or to design a device, so in that case, again you have to analyze the problem and you have to identify you have to do the corresponding design. While doing the design, you should able to identify which type of programming you have to write, whether gate level or data flow or behavioral or switch level, so that you have to analyze and you have to use it. After designing or analyzing, then again you will be testing using the modern tool. And while doing this, you will be doing either teamwork or individual with the communicating with your friends or with your faculty and all. Okay, so that's why CO3 also strongly maps to PO3, PO4, PO5, PO9 and 10. And CO4 maps to again the same PO3, PO4, 5, 9 as well as 10, because tasks, functions and directives. So as the design matures, means as the complexity increases, then we have to write program in a smart way. So when we are writing program in a smart way is nothing but reducing the number of lines required to write the program, to get complete functionality of the device, and in a more effective way we need to write the program. So that is why we are going to consider again, we need to think what type of functions we have to write, what are the required directives we have to use, which part of the code can be considered as a task and which can be considered as a function. All these things will be analyzing and we'll be designing. And again the same thing, after designing you need to check whether your design is proper or not. So we need to go for analysis using the modern tool. And if we are using the modern tool, obviously we will be doing either individual or teamwork. And also when we are doing teamwork we will be having communication skill. And why this particular course is not mapping for PO6, 7 and 8 is, here we are not going to discuss anything related to ethical issue or anything related to solution for societal problem in this course right now. And next we are not discussing anything regarding to sustainability of the design what we have done. Okay, because in your course basically we are trying only the circuits which you have learned in digital electronics in third semester. So that is why, since we are considering only simple circuits, we are not discussing all these things. And similarly, when I come for PO 11 and 12, so here we have not conducted, we are not doing any big projects by considering this Verilog HDL, and as a result, we have not mapped to PO 11. And lifelong learning, it depends. Suppose if you people are joining for any particular core companies and all, there you will be able to use this repeatedly, otherwise you will not be using. So that's why I have not mapped this to lifelong learning also. And the last CO what we are having is interpret various constructs. So here we are just interpreting how the synthesize will going to develop the circuit. We are not uh, developing any circuit here. We are just analyzing how cat tool will going to develop the circuit for a given commands or for a given program. So that is why that gives only the engineering knowledge, and it will not map to any other POs. And when I consider PSO mapping, so here, since we are considering only digital circuits, and we are not considering any communication part and all, so our course will mainly map to PSO 1, not for PSO 2. Okay, so this is how we have considered COPO mapping. Why these particular mappings has been done, that justification I have given. Okay, if you are having any doubts you can ask. Next, let us consider the first module. So when we are considering the first module, so the first module is overview of digital design with Verilog HDL. So when we are considering this circuit, this particular unit, so here mainly we will going to consider how the CAD tool has evolved and what is the need for the CAD tool and what was the need for the hardware description language, which language we are going to use. All these things we are going to discuss in this module, in this unit. So these are the corresponding contents what we are having for this unit. So first, before considering the evaluation of the CAT tool, so first we have to consider what was the problem faced by the designers. So here in this image we can observe that the discrete component like a transistor, and similarly here we are having vacuum tube transistor and all, and also in this bread In this board, you can see that how the discrete hardware components are connected and how big each components we are having, like capacitors, transistors, relay. All these things we can able to see here. Okay, so now first let us analyze the need for the CAD tool. So let us consider here, if I consider a transistor. So when we are considering a transistor, it we know that basically, let us consider an NPN transistor. So in that we are having emitter, base, collector, three particular uh, parts. So now when we are applying input voltage between emitter and base, and we can observe the output across the collector. So here the current will going to flow between this base and collector only when there is a current flow between emitter and base. So these are the corresponding junctions what we are having. Okay, so until unless if you are considering NPN transistor, so this will be of N type and this will be of P type, and this will be again collector will be of N type. So when there will be flow of current if this PN junction is forward biased, and again if this PN junction is forward biased, then there will be a flow of current between this junction as well as this junction. So when I need to consider the flow of current, so here N is connected to, sorry, so N must be connected to the negative terminal of the supply, and base P is nothing but it is having maximum holes, and N will be having maximum electrons. So when there will be a flow of current between emitter base junction, when holes from the base has to penetrate through this junction to emitter, and electrons from the emitter has to move to the base. So when the base emitter junction is forward biased, so when there is a forward bias condition, in that case the electrons present in the emitter will be moved to the base, and similarly holes present in the base will be moved to the emitter. And now when the number of electrons increases here, so here also we can see that this is a PN junction, right? So here as the number of electrons increases suddenly, so it will going, since base is also connected to P, and collector is connected to negative terminal through the load. So here we will be having the corresponding supply. So collector is connected to negative terminal through the load. Again this junction is also forward bias, so the electrons which are collected from the emitter will be flown to the collector. So as a result, current will move between emitter and collector. So when the base current is removed, for example, when the base current is removed, then this junction will not be forward biased. So when the junction is not forward biased, there will be no flow of current between emitter and collector. So as a result, we will be getting this as a output characteristics, that is input voltage versus output current. So when the base current is 0, that is the voltage between base and emitter, so increases as the voltage between base and emitter increases, then there will be a increase in the flow of current. If the voltage between base and emitter is less, then the device will be in turned off off condition. So as a result, here we will be having the cutoff region. When the base current increases, the corresponding collector current will also increase. So as a result, the current will be rising from minimum to maximum. After certain voltage, the collector current will become almost constant. Even though if you increase the base current, the collector current will become almost constant. So that indicates that the it has reached the active region, means where the transistor is completely turned on. So when the base current is 0, the transistor is turned off because there will be no flow of current between emitter and collector. But when the base current is given maximum, the transistor has been turned on completely. So as a result, maximum current will flow and the amount of current will remain constant. So that is known as active region. So depending on this and the more depending on this, we can consider transistor as a switch. So when if I want to turn on the transistor, I need to give base current. If I want to turn off the transistor, I need to remove the base current. So as a result, transistor can act as a switch, and this switching property is used to design the logic circuits. So when we are going to consider logic circuits, for example, let us consider a simple AND gate. So when we are going to consider a simple AND gate, so in that case, we can observe here the voltage is connected to the voltage VCC is connected to the transistor A, and again output of transistor A, that is collector of transistor A, is connected to the emitter of transistor B, and at the collector of transistor B we are measuring the output. So now if both the transistors are turned off, there is no flow of current from VCC to ground. So as a result, when both A and B are 0, the output is 0. If either A is turned on or only B is turned on, again there is no continuous path for the flow of current. So we will be getting the output as 0. When both the transistors are turned on, then there will be a flow of current from VCC to ground. So then the output voltage will be equal to 1. So this operation is nothing but AND operation. So to get logical AND operation, we are going to use transistor circuit which I have mentioned here. Okay. Similarly, if I want to consider not operation, so in that case, what we are going to do here, we can observe the load has been connected uh, to the emitter of the transistor. So as long as the transistor, means when A is equal to 0, means there is no base current. When the base current is 0, there will be no flow of current. So the output voltage will be maximum. If I turn on the transistor, there is a flow of current between VCC to ground, and the output voltage will become minimum. Means when A is 1, the output is 0. When A is 0, in that case output voltage is maximum, so it will be equal to 1. So now let us consider XOR gate. If I want to consider XOR gate, since it is a combinational gate, it can be written as A bar B plus A B bar. So here, when I consider this expression, what we can observe? We need an inverter to perform A bar or B bar operation, and we need an AND gate to perform A bar B as well as A B bar, and similarly an OR gate. The OR gate operation can be observed here. So here what we can see is these two transistors are connected in parallel. Okay. So when both the transistors are turned off, there will be no flow of current between VCC to ground. Suppose if any one transistor is turned on, let us consider when A is equal to 1 and B is equal to 0. So in such case, what happens? Suppose when A is turned on, means current will going to flow in this path. Okay. So as a result, we will be getting voltage across the load. Till then, voltage across the load was 0. And now, voltage across the load is maximum. The same thing happens when A is 0 as well as B is 1. So in that case, current will flow in this path. So when the current flows in this path, then also output voltage is maximum. If both are turned on, what happens? Then also current will flow in the same path. So we will be getting output voltage as maximum. So this is the circuit for OR operation. Now, in order to implement XOR operation, how many transistors are required? Here we need to perform two inversion, that is A bar as well as B bar. So we need two NOT gate. For one NOT gate, one transistor means for two NOT gates, two transistors. And similarly here two AND operations is there. One is A and B bar and the another one is A bar and B. So for each AND operation we need at least two transistor. So for two AND operation we need four transistor. Similarly, to perform OR operation, we are having only one OR operation. So we need only one OR gate, which consists of two transistors. So totally, we need 8 gates for one XOR operation. Now, you imagine if I want to perform half adder. So when I want to perform half adder, so in that case, for sum, I need to consider sum will be equal to a bar, that is nothing but a b bar plus a bar b, that is a XOR b. Okay, so as a result, we need XOR gate between the inputs A and for the inputs A and B, and similarly for carry it is nothing but A and B. So when we are going to perform A and B, so we need AND gate. So for AND gate we need two transistor. So totally how many transistors are required for half adder? For XOR gate 8 transistor and for AND gate 2 transistor. Totally 10 transistors are required. And we have to connect those transistors using these type of discrete objects. So such 10 transistors and the corresponding interconnection and also the corresponding load we have to place, because if we do not place any load resistance then there will be a short circuit. So all these things we have to do to get one half adder operation. Similarly, if I want to consider full adder, so what happens when we are going to consider full adder? So in that case, we need for full adder, we know the expression, that is we will be having three inputs A, B as well as C in. So the expression will be A XOR B XOR C. So the two XOR gate or two XOR operations will be done. And similarly for carry we are having one simple expression, that is nothing but AB bar plus AB plus BC plus AC. So here 3 AND operation and 2 OR operation. So for every AND operation 2 transistors and for every OR operation 2 transistors. So as a result we need totally 10 transistor to calculate carry, and to calculate sum we need 2 XOR operations. So we need totally 16 gates, 16 transistors. So totally how many transistors? 26 transistors are required for only 1 bit full adder. Now let us analyze. If I consider 4-bit parallel adder, how many transistors? You can imagine the complexity of the circuit. When you are doing the circuit in the breadboard, this you might have experienced in the digital lab as well as analog lab. When we are going to do circuit in the breadboard, if as soon as we do immediately we may not get the proper output, because if there is some loose contact or if the connection is not correct, in such cases we need to debug all the errors and we have to check the functionality. So as the circuit complexity increases, finding the fault present in the circuit will be difficult. So for that, what we are going to do, we the designers need that some cat tool or some help which will do the work automatically without the assistance of a designer. So that was the requirement for the development of the cat tool. So when we consider any design, so in that case, first you have to do a floor planning, means sorry, first you have to take a pen and paper and you have to write the design in a very abstract manner, means what operations has to be done, and the next thing how each operations can be done, and then finally we will going to consider which, for every part, which type of circuits we have to use and what components are required for those parts and how to implement that. All these things we have to write down, and then based on that we have to write the circuit, and after writing the circuits we have to take those discrete components, we have to make connection, and we have to check the functionality. If it is working properly, then we'll go for printed circuit board. You might have heard about that, because why we will go for PCB? There, in a small space, all the components will be placed, and also the interconnections will be done on the board only, so that external wire mm, uh, will not be there. So connection error can be reduced. In this circuit only, in the second circuit only, you can observe this is the corresponding printed circuit board we are having, and in every particular location where the sockets are available, the corresponding components are placed. Suppose if the same circuit is designed using a breadboard, then it would be difficult to analyze if there is any error, isn't it? So that is why the complexity of the circuit increases. So now the designer felt that some automation is required. They can able to write the corresponding circuit on a piece of paper, but it has to be bought into the integrated circuit, or the layout of the circuit should be done automatically. So for that, cat tool came into existence. And now to interact with the cat tool we need some language, right? So that is why this Verilog HDL or VHDL came into existence. So now I'll just take a simple example. So using just now we discussed regarding the circuit complexity of the half adder, full adder and all. So now if I consider discrete component, again it's a difficult to maintain and difficult to connect. All these things, difficulties will be faced. So now to reduce this difficulty, first we considered the corresponding integrated circuit. So initially small circuits were built on the integrated circuit, that is IC, and when once it is working properly, then the corresponding circuit integrated circuits are used in the design. So here let us consider this image. So in the first image here we can see that small gates and all. In digital electronics lab also you might have used, isn't it? You have used two input AND gate, NOT gate, XOR gates. All these gates you have used, they are all the ICs, isn't it? So in those gates, simple circuit, because if I consider a two input AND gate IC, so in that IC we will be having four two input AND gates. So each input will be, I mean, each gate will be having three terminals, one output and two input. So totally we will be having four gates, means we will be having 12 input output pins, and next power supply VCC and ground another two pins. So totally 14 pin IC we have used, isn't it? So in that IC only four AND gates are placed. So let us consider in terms of transistors. So for every gate two transistor, means for four gates eight transistors. So only those many transistors are present in that IC. So now as the complexity increases. Means if I consider shift register, so again register, if I consider register, I need to take flip flop. If I am considering flip flop, again I need to using the basic gates, flip flop will be designed. And again for basic gate, I need to design using the transistor. So as a result, the complexity by using the transistor, the number of transistors used in the circuit was keep on increasing. So for that, the IC, inside the IC, the number of gates, if we keep on, if we increase, in that case more and more circuit can be placed in the same IC. So how to obtain that? So for that, what we did is, initially with the less number of gate counts, the ICs were built. Later, as the technology gets sophisticated, means as the technology improves, the number of gates in the same size of the integrated circuit, means in the same area of the IC, the number of gates was increased. Means even though if I reduce the size of the transistor, I am able to get the same functionality. When I am able to get the same functionality, then instead of using larger area for a gate, I can reduce the area and I can accommodate more gates. Similarly, the miniaturization means as the technology improves, the size of the gate was keep on reducing. So as a result, more and more gates are placed inside a single integrated circuit. So this is in the second diagram, you can see this is a very large scale integration we are going to call. So here around the more billions of circuit transistors are there. So as a result, from small scale integration to super large scale integration, the IC levels, different levels of integration circuits were considered. So now let us consider the corresponding levels of integration. So here initially, as I showed in the diagram, a small scale integration was done. So in that the number of gate counts was 2 to 50. So only small number of gate counts we are having. And the next one what we are having is medium scale integration, where the number of gate counts inside the IC can vary from 50 to 5,000. Similarly, for large scale, still more, that is 5,000 to 1 lakh. And similarly, if I consider VLSI, from 1 lakh to around 10 lakhs, it was the gate count was increased. But if I consider ultra large scale or else in super large scale integration, in that case, above 1, yeah, above around 1 billion gates were present. So as a result, if more number of gates are there means I can incorporate or I can place more number of circuits inside that. So when more circuits can be placed means the corresponding designs for every part of the circuit can be placed properly, and multi operation can be done through a single integrated circuit. Okay, so this is how we are going to consider the different levels of integration. Now also we are having all these levels because depending on the requirement, whether we need less number of gate counts or more number of gate counts, we will be selecting any one of these level of integration according to the requirement. And one example what I am willing to give is, you can see the motherboard of the computer. So when you see the motherboard of the PC, so there you can see small ICs, larger ICs, all these things, different size ICs, even for RAM, ROM, everything it will going to vary. That again depends upon the requirement, the corresponding integration will be considered. Okay, this is how evaluation of the CAD tool came into existence. So that is why when we are going to consider the CAD tools, mainly the automatic design will be done by the CAD tool. So we first the designer thought of electronic design automation means if he is able to describe the requirement, the corresponding software has to design the circuit automatically. So that is why we are going to call the electronic design automation. So it has to design the circuit by itself. So after that, once again, breadboard verification. So the after design has been finalized, according to that, once again we need to check whether the design is working properly or not. So previously designers used to check using the breadboard. So again, the verification of the design came into existence. So when the verification of the design came into existence, synthesis tools will be had been considered. So that is why here in the back end the design used to be developed, and in the front end here we used to do the simulation as well as synthesis. So in common we are going to call CAD as well as computer aided engineering as electronic design automation, because using both front end and back end only we can able to design the IC through this automation process. So that is why commonly we are going to call these two as electronic design automation. So after this only we came across very large scale integration means thousands or billion lakhs of gates used to be placed on a single IC, and a complex as a result more and more complex circuits were placed on a single integrated circuits. Okay, so any doubt in this? Yeah. So till now we have discussed in this class we have discussed regarding the corresponding CO/PO mapping and the corresponding course outcomes. And the next we have discussed why the evolution of CAD tool came into existence and what was the complexity faced by the designers. Okay, all these things we have discussed. In the next class, let us discuss the how actually the wafers are considered, how IC is grown on a wafer, and how the design will be, I mean, how the integrated circuit is manufactured. Okay, and all the corresponding design methodologies let us consider in the next class. Okay, any doubts?